Now we're going to take a look at Rolle's theorem. You may remember that from calculus. And the way I think of it, or an application of Rolle's theorem, is that you're in your car on a road, and between one stoplight, you're stopped at one stoplight, then you accelerate, you proceed, and then you stop at the next stoplight. So your speed was initially 0, and at the end it was 0. Somewhere in between there, you reached a maximum velocity. And that's essentially what Rolle's theorem is. Your velocity increases, reaches a plateau, a relative max, and then it declines. Now it may go up and down several times. You may have several relative minimum and relative maximum points along the way. But at some point, you're going to reach a relative maximum. And I guess you could think of it, I guess it's hard to think of it in using your car where you're using negative speeds. But just think of it as being a function. If you start off at 0, if you go downward and then come back up to 0, you're going to have at least one relative minimum. If you go above the x-axis, starting at 0, go up and then back down to the x-axis, you're going to have at least one relative maximum. And that's what Rolle's theorem says. It says, let function f be continuous on a closed and bounded interval, AB, and differentiable on all the interior of this closed interval. If the value of the function at the endpoints a and b are both 0, then there's a c somewhere in between that has a derivative being equal to 0. So let's take a look at the proof of Rolle's theorem. And the first thing we're going to do is get the very, very simple case out of the way. If f of x is the constant 0 function on the interval AB, then the derivative is also 0 on AB, and we're done. We found an infinite number of points where that would be true. So otherwise, the else part of this, there is some value of x where f of x is not equal to 0 in this interval. Okay, well, now the domain being compact, and maybe I'll put it in, I'll go ahead and write it here, f continuous. That implies that there is an x1 and an x2 somewhere in the closed bounded interval AB, in the domain, where the function f attains its minimum and maximum. So there's an x1 and an x2 such that f attains or reaches its min and max values, respectively. So x1 would be the min, where the min occurs, and x2 would be where the maximum occurs. Well, we only have a couple of more sentences here. Since one of x1 and x2 falls in or is in the open interval from A to B, why can I say that? Well, it's not constantly 0. F is not constantly 0 on the closed and bounded interval AB, and that's what I'll say. F is not 0 on all of AB. So one of them, it's possible that x is, that it reaches either the min or the max, one of them, say at an end point, but the other one is not going to be at an endpoint. So one of these is internal to or in this open interval from A to B. Since that's the case, assume it's x1. The proof would be nearly identical if it were x2. So we're assuming x1, which is the minimum value. Well, by the previous theorem, by theorem 4.6, the derivative of f at this point is 0. And that's all we needed to prove. The C we found was this x1 that we constructed here.